So in this video, we're actually going to look at annihilation, which is something I mentioned a few times in our last video. So when a particle and its antiparticle meet, they annihilate each other and convert all of their mass energy, that is to say we remember that mass and energy are basically the same thing, related by E equals mc squared. So they convert that mass energy into radiation energy as photons. So we think about it really that we have these original particles, they collide, they annihilate, and we're left with this with these photons instead. So we lose these particle-antiparticle pair and get photons out. So just label that. We could have that this is our particle, and this is our antiparticle, and these are our photons, and this is where they collide. So the first thing to note from this diagram is that two photons are created, and we need that for conservation of momentum. Now, this is something we're going to talk about much more later, but the idea for now is that particles basically have this thing called momentum associated with them, which is their mass times their velocity, and that's always conserved. But actually, this particle here, well, that's going to have a momentum of mv. We'll say this direction is v, and so if we actually had that this particle was colliding at the same velocity but the other way, so this would be m minus mv would be its momentum, we'd have that our total momentum would actually just be 0. And to have a situation afterwards that would also have 0 momentum, you can't have that with just one photon. You must have two photons produced. So just to sum that up, if our momentum before is 0, that implies that our momentum afterwards must also be 0, and that's impossible with just one photon. So that's why you have to have these two photons produced, travelling, in these opposite directions to make sure that the total momentum afterwards is also 0, just like it was before. So now we know that we basically produce two photons. How do we find the minimum energy of each of these photons? Now, why do I say minimum? Well, it's minimum because the faster those particles move, the more energy they have. As I say, if this particle was to basically be travelling at twice this velocity here, it's going to have more energy. And so having more energy means that there's going to be more energy given to the photons. And so what we kind of do with the minimum is just think about it coming from just thinking about the rest energy of the particle. That is to say, if they were barely moving, if they weren't moving at all, and then they interacted, collided to annihilate, so they're not moving at all and then they annihilate, that's going to release the photons with the minimum amount of energy. So for instance here, they're barely moving, and that's going to release this kind of photon, it's kind of energetic but not really energetic. And then when we see they're moving very quickly, when they collide or annihilate, I've just drawn in here that's what I mean, this is where they annihilate, and obviously there's two photons produced. I've just done this because I'm just trying to show what the energy of each of the photons is going to be like.
Hey guys, to continue watching this video and unlock hundreds of other super concise and exam board specific A-level physics videos, just click the Snap Revise smiley face. Join me today, and together let's make A-level physics a walk in the park.